Armed with the RIP and with the understanding of its properties, we are now ready to address the stability issue of P0 epsilon. Let's define our goal. We start with an S-sparse vector x naught and multiply it by A, getting the vector B naught. This vector is contaminated by an additive noise V of epsilon bounded norm, and this results with the vector B. We use A, B, and epsilon to define the P0 epsilon problem. Let's just assume that we are able to solve this problem, getting x hat. Clearly the cardinality of x hat is S at the most. Our question is, how far is x hat from x naught? Our analysis of the problem repeats some steps we have already seen, so let's go through them quickly. The vector x hat obeys the epsilon constraint, and it is of cardinality upper bounded by S. Thus, we know that the distance between ax hat and ax naught is 2 epsilon at the most. And we also know that the cardinality of x hat minus x naught is no bigger than 2s. So, defining D to be the difference vector x hat minus x naught, we have that the norm squared of A times D is smaller than 4 times epsilon squared, and D has no more than 2s non-zeros. Using the RIP, and more precisely the left-hand side in its definition, we get that the squared norm of A times D must be lower bounded by 1 minus delta 2s times the squared norm of D. From here immediately follows that the norm of D squared is lower bounded by 4 epsilon squared divided by 1 minus delta 2s. Since delta 2s appears in the denominator and with a negative sign, replacing it with something bigger leads to an upper bound on this expression. So, as our last step, we replace delta 2s by a mutual coherence upper bound on it, 2s minus 1 times the coherence, and we get to our final result. Note that this expression is correct as long as the denominator is positive, and that implies that this result is valid only for s below 1/2 of 1 plus 1 over mu. That's it. We are done. We just got a stability result. And here it is posed as a theorem. It says that x hat is not far from x naught, as the distance between the two in L2 is small, proportional to epsilon. So what do you think? Should we be happy about this outcome? Observe that the distance between x hat and x naught is at least 4 times the energy of the noise. So are we getting noise magnification? This increase of the noise is an artifact of the way we have chosen to prove the stability property. Assuming that V has a bounded noise means that it can be anywhere in this sphere, and this makes it an adversarial noise that chooses the worst realization to fight us. There exists an appealing alternative in which V could be assumed to be random, and then the results that can be proven are far more optimistic. If, for example, we assume that V is white Gaussian noise of 0 mean and sigma as its standard deviation, then the energy of the noise vector is n times sigma squared. In this case, one can prove that the deviation of x hat from x naught is of the order of s times sigma squared multiplied by a log factor. This means that a strong denoising effect is obtained. Such a result is typically posed with high probability and not deterministically as our earlier statement. The reason we have not shown this result here is simply the fact that such an analysis is more involved. Another interesting question we leave as open at this stage is this. Could we prove that P0 epsilon succeeds in recovering the locations of the non-zeros in x naught? This is a different measure of success, and definitely one that is worthy of our attention.